that anyone has a question or anything about before we get going? I tell you, getting back to my long-haired hippie days is forgot me. It's only been 52 years, I think, since I had my hair this long before, and that was graduating from high school and getting ready to enter college. And then, you know, for a time there, it was really short because when I was in the Army, Company D, 1st Battalion, 3rd Infantry, I was in the Old Guard up at Fort Myers in the early 70s. And we had shaved twice a day, complete shaves, and 2 haircuts a week down to 1/8 of an inch. So once I got out of the Army, I started growing the beard back and haven't had it off since then. My wife's seen me without my beard once, and I took it off for some insane reason, put it right back on. But otherwise, it's been with me since then. So anyhow, it's bugging me now, so I keep having to do this. So hopefully you won't be distracted by that. All right. So let me well, first, as I just said, is there any questions or anything before we get going? Okay. I'm going to share out the data file, which I have already loaded into JASP, and it's up, and so there it is. Yeah, okay. There is the data file, and get myself a little pointer here of some sort. All right. A little bit larger, maybe. And since I've already run these things, I already have the analysis part done, and I already have the output, and I've given you an output file, a print output file, just in case. But let's open up the descriptive piece here. And in the descriptive piece is obviously the things that you're always kind of looking for, interested in, are the basic information: mean, median, standard deviation, minimums and maximums. I don't know why those are defaults all the time, but they're really not of great interest, but they always show up. The only stat that I added in here that was different from what was the default was that I checked on the median. And by checking on the median, I generated the median output for this particular GPA. Now, I did that for a purpose, because the means and the medians in a perfectly normal distribution would be the same. And if they're different, then it's not perfectly normal. In this case, it's not unnormal enough to worry about it too much. But most of the time you don't. But what it does show is how you account for skewness. And the other thing that I added in, which you will not have to use on the final exam, I promise, was distribution plots with display density. And what that does is it gives you this bar chart. I guess it's not bar, I guess it's whatever the other direction is. And the line, which gives you kind of a distribution line. It's kind of the average of, each of these distribution blocks. And if you'll notice, the mean is less than the median. The mean is 2.64, and the median is 3.0. Now, What normally when we look at a distribution, we talk about, if we talk about anything, we talk about the skewness of the distribution. You know, is this distribution skewed one way or the other, or is it relatively normal? Well, this one is skewed low. And if you think about where the median is, at the median point, there are 50% of the cases above, 50% below. So 50% of the cases are in these two bars here, and 50% are in these bars down here, plus half, probably about a third of this one here. And skewness generally is defined by which direction the mean is from the median. If the mean is below the median, we typically understand that it is skewed low or to the left-hand side of the distribution. If the mean happens to be above the median, then we typically think of it as being skewed high. But visually, when we're talking about skew, we typically are talking about there's kind of a high short tail, and then there's a long low tail. And in this case, the mean is lower than the median, so that is skewed in this direction. Now, that's in and of itself not greatly important, but it does help you think about how normal this distribution is. Yeah.
Is the proper terminology and wording to use when talking about skewness, like when we're working on our assignments, skewed low, include skewed low, skewed high, or do you want discussion about long tail, short tail?
Nah, I forget about the tail stuff. Just,
okay.
You know,
so just whether it skews high or skews low.
Yeah.
Okay.
And that's what you'll find in most articles or research reports or things like that. They'll talk about the skewness in fairly general terms, and they'll say it's okay, it's either low or high, or some of them will even say left and right. But it's you talk about it in the simplest of terms, because typically when you're working with descriptives, you're not terribly worried about if it's not perfectly normal. You just want to know, what are the numbers that can represent this thing. Now, the other thing that's on here that's important to know is a standard deviation, because that allows you to talk about interpretations of what's in the middle 95% or what's in the middle 68%. And 95% is the mean plus or minus 2 standard deviation units, and 68% is the mean plus or minus 1 standard deviation unit. Now, ignore minimums and maximums. I mean, that's typically a mistake that people make. You think that minimums and maximums somehow define something. They don't. They just define what's the lowest score and the highest score in the data set. Otherwise, they're pretty meaningless stuff and kind of trivial, and lots of places don't even kind of mention those. Or a lot of work doesn't even mention those. Or a lot of tables won't even produce those. They'll just cross those out or blank those out. But it is, in terms of descriptives, this is about all you ever are going to need, is a table that's got the mean, median, standard deviation, and Now, another thing that's in here that I'll just mention once again, just for information, is you notice there's a difference between valid and missing data points. Valid means that there are 100 or 1,172 subjects in here that have complete data sets. In other words, all the data points that were this particular data point about GPA second semester appeared in 1,172 files, and it didn't appear in 252 files. So there's 252 cases in this particular data set that doesn't have this bit of data in them. So that's all missing means, is that there's not complete data sets for the the variables being analyzed. And that's about all you need to know about the descriptive statistics. Is there any, we're all good? Yep, okay. Then we went on and we talked about the independent, we talked about the various t-tests. Now, oh, I know one thing I should have mentioned up here. Z-scores. If we're talking about Z-scores, all we're talking about is individual scores defined by that individual score minus the mean divided by standard deviation. And that's all the Z-scores talk about. And I don't think I put it on that final or not, but I don't think so. Independent samples t-test. Remember, that's when we have two groups. We have a continuous dependent variable and two groups. And we want to know, is there a difference between the two groups? In this case, I picked GPA semester 1. This data file was about looking at 3 years worth of entering students, the amount of adjunct instruction they had during their first semester, and whether that had impacts on other things like their GPAs at the end of the first semester, second semester, end of the first year, second year, final GPA, and stuff like that. It also has other markers in there for whether they graduated or not, whether they were in developmental programs or not, whether they were part-time or full-time students. And so there were different, other elements in there, but a lot of it was GPAs and things like that, and credits taken and that sort of stuff. And so the question I'm kind of answering here is there a difference based on sex or gender on first semester GPA? Simple question. And when I didn't change much in here, the only thing that I added was descriptives. And I think that's all I added. Yeah, all I added was the descriptives. And so if you look at the output, the p-value is less than 0.001, so there is a significant difference between males and females. And when you look at the descriptive stuff, you see that females had a mean value of 2.76 on first semester GPA, and males had a mean value of 2.519. So in essence, all we're saying is that females had significantly higher GPA on their first semester than did males. And there's pretty large N's for both of them, so we're not worried about any real discrepancy in cell sizes here. Normally, you'd like these N's to be close, but when the N's get large, it's really doesn't mean as much. If the N's were 20 and 40, that'd be a problem. You'd like them more, 30-30 range. But when the N's get really big, it doesn't, this difference is not a big deal. And so the answer to the question, is there a significant difference between males and females on first semester GPA, is that yes, and the difference is that females had significantly higher GPAs at the end of the first semester. Okay. All right. Then the next question that I asked was there a difference in terms of GPAs during the first semester and the same students' GPAs during the third semester? Is there a difference between those GPAs? And because we're looking at the same subjects, two different measures on the same scales, it's a paired samples t-test. The t-value is less than 0.001, so it's a significant outcome. The nature of the outcome, because I had plopped in descriptives, the nature of the outcome is that first semester GPA was significantly higher than third semester GPA, or conversely, third semester GPA was significantly lower than first semester GPA. And that's not terribly inconsistent with what we know about students' GPAs. That they tend to, the first semester tends to be, they're trying a bit harder, and teachers are maybe a little bit less rigorous in grading and things like that. But by the time they get to the third semester, they're in some slightly harder courses, and people are a bit more rigorous, and sort of thing. And so the GPA went down significantly from first semester to third semester. Questions? Okay. One sample test. If I ask this question, if the first semester GPA among all students in the community college system, was 2.75, were the students in this college significantly different from the system? And that's a one sample test, because I have one sample and I have a population parameter to compare it against. And so the one sample test turns out to be significant, 0.003, less than 0.05. And the first semester GPA for this college was 2.65. For the entire college system, community college system, is 2.75. And so students at this particular college, first semester GPA was significantly lower than the system-wide college, or system-wide average for first semester GPA. So it's not enough to know that, there is a significant difference there. You always have to talk in terms of directional differences. And that's why it's really important to make sure that you've clicked into the descriptives, which is right on the first page of the t-test analysis selection section. So it's pretty easy to plug into those. And that brings us to the end of the t-test, which pushes us over into ANOVA, because we have more than two groups. And actually, in this particular variable, we have 6 groups. And these were the 6 specific categories of data that we collected during the early 2000s on ethnicity. Now that has changed, and the federal, the brackets have changed, but this was what we were doing in the early 2000s: American Indian, Asian, Black, Hispanic, non-specified, or white. And so once again, we'll look at this first semester GPA, and we'll decide whether ethnicity is if there are significant differences based on ethnicity. The only thing we plugged in here is the descriptive statistics. And down here we have post hoc test. I slid the ethnic variable name over from the left-hand box over to the right-hand box. That means that's what we're going to test on the post hoc test. And we left the defaults as standard and the defaults as a Tukey. Now, in reality, what the Tukey means is that we're assuming that this first semester GPA is reasonably normally distributed. And if this were the only analysis we're doing, we would probably want to check for that. And there are ways of checking for that. In fact, on this thing, there's what's called an assumption check. And under the assumption check, I can check for what's called homogeneity. Well, that means normal distribution. That means the samples look like they were drawn from relatively normal distributions. But we didn't do that. We didn't worry about that because normally you don't, unless this is the only analysis you're going to do, then you would do that and follow the cues from there. But we found that there is let me get this back now. We found that there is there are is/are, but there are significant differences between groups on ethnicity. And so we go in the descriptives, we get, a pretty good notion of the means. Now, when we look at the ends and we realize, for example, American Indian is only 7, we're not going to really worry about that. We're not looking for any differences there because all the other ends are higher. And that's so far lower than the rest, we'll just kind of ignore that and not even look at those. And so, down in the post hoc test, we can ignore all this American Indian block up here. We'll just not look at that. Asian is not significantly different from any of the other ethnicities. All these p-values for the Tukey, none of them are significant. Black is not significantly different for Hispanics, Asians, non-specific, but it is significantly different from white students. And Hispanics are significantly different from white students. And so if you go back up and you look at, white students 2.74, Hispanics 2.104. So Hispanic students are significantly lower than white students on first semester GPA, and you look at black 2.29, black students are significantly lower than white students on first semester GPA. And so those are the only two relationships in here having to do with differences between white and Hispanic students and white and black students. I mean, you could see the same thing down here based on these mean differences, but it can get a little confusing. It's just much easier to look back up in the descriptives and look at those comparisons that you've identified down here up in descriptives. Okay, we're good. All right, sailing right along. Correlation. If I ask the question, is there a correlation between the number of credits that a student took first semester and their first semester GPA? And, you know, it would be interesting to know where did correlation go? I seem to have lost the correlation output. Nah, there it is. Okay. I went too fast. And so I slid those two over in the variables. I didn't change anything down here. And when we looked at the correlation between first semester GPA and credit completed first semester, we get an R value of 0.257, which is significant. And so, yes, there is a significant relationship between number of hours completed and first semester GPA. Now, it's a positive correlation because the R is positive. It's not a negative 0.257, it's a positive 0.257, which means as the number of credits completed goes up, the GPA goes up. So students that take more classes, more credits, have higher GPAs. Now, in and of itself, that doesn't say much of anything, except there is a relationship there, and it's something worth exploring to understand why or what's going on. You know, students are taking more credits while they're getting higher GPAs. I suspect it's because students that are in developmental courses or whatever are not allowed to take as many credits in most cases, and we'd have to explore that to figure that out. But all this tells us it's a positive relationship. The R is 0.257, and it's significant because the P is less than 0.001. But it is a relationship. It's not a cause and effect or an inferential statement. It's just that these two things are related. Any linear regression? Let's see if we can figure out if the credits completed during the first semester can help me to predict their GPA at the end of the year. Now, we already know they complete more credits first semester, they have higher GPA first semester. Does that carry through the second semester into the end of the year? And so it's a linear regression. We didn't change anything in the model. We included the intercept. That's important to have the intercept in there. We didn't change anything in terms of the statistics. We didn't change anything in terms of the methods. So the only thing we did is in the model, we added in to include the intercept. And so our output for significance, we look at the ANOVA around the whole model. And the ANOVA is significant, 0.001. So it is a significant prediction equation. It is a significant predictor. And if we were going to build the equation, we have what we need in the coefficients table under the unstandardized coefficients. So if we were to build an equation, it would be cumulative GPA first year excuse me, is equal to 0.0222 times credits completed plus 2.68. So it would be 0.022 times credit completed plus 2.648. And that would be the prediction equation.
Dr. Bolt?
Yeah.
Why don't you use the 2.819?
Because that's if there's no, if you're assuming that there's no predictor there, that it's not a significant predictor. Well, it is a significant predictor. So we're going to use the alternative hypothesis, or the H1. Don't think about these P's out here. Don't worry about these out here.
So is it standard practice just to look at the alternate hypothesis first?
If it's a significant prediction equation. In other words, if the ANOVA is significant and tells you, okay, it's a significant predictor, then you know the null hypothesis doesn't mean anything. And so the information you use is off the alternative.
Thank you.
I know it's where some people in stats and some people in research are now kind of lobbying for us to just stop talking about null hypothesis and alternative hypothesis and things like that, as if they're kind of obsolete, or we don't, they're not needed anymore. So, but it does, as a purist and as someone that kind of understands philosophically why we have them set up that way. I hope we hang on to them. But yeah, if it is a significant predictor, then, and that's defined by the ANOVA up here. If the model, the H1 model is significant, then we use the information from the H1 model down here.
Thank you.
Okay, other stuff? Okay. And that brings us to looking at categorical information and what are generally referred to as non-parametric statistics. In other words, when we're only dealing with categorical information, we call those non-parametric, because parameter roughly means that we can get means and standard deviations and all that sort of stuff out of the data. But when we can't, when they're all categorical, then we have to use what are called non-parametrics. And the primary non-parametrics is the simplest one is chi-square. And in chi-square, the way we get there is that we start with contingency tables out of frequencies. Now, in some statistical programs, that's also called crosstabs. Contingency tables and crosstabs are, for all intents and purposes, the same thing. There's a little subtle difference there, but for most of the basic stuff, it doesn't matter. And once we got into the contingency tables off of frequencies, the question we're asking is retention after the first year related to the level of adjunct instruction that they took in the first semester. And so it doesn't matter really what you put in the rows or what you put in the columns. I tend to want to put the simpler, you know, the one with the less levels to it. I tend to want to put that in the rows and the more levels in the columns. And in this case, retention has 2 levels, yes and no. And adjunct level has 3 levels, less than 25, between 25 and 75, and more than 75.
I
And
got a
so,
question, Dr. Bolt.
yeah.
How could you tell the adjunct levels, like the number of years? Is that somewhere in JASP that I'm just not seeing?
No, I didn't give you the code book for this, and that's
Okay.
why I'm telling you that now. You generally would look in that code book, like for the finals, the data set for the finals. If you want to know how many different marital statuses there are and what they are and where they live geographically, you would go back to the code book, code sheet you have, and you would look to see what those levels mean.
Okay.
And I just didn't build out the code book for this because, you know, I figured I could explain it simply enough. But yeah, that comes typically in the code book. And so the adjunct levels are up to 25%, 25 to 75, and over 75. And there's a reason, there's a long reason for why it's, the brackets are not equal increments, and I won't get into that, but for the sake of argument, let's just say that they're legit looking at them that way. And the chi-square is the test. It's always the test for contingency tables. It will be the default value, and so you don't typically have to add it unless you turn it off for another analysis. But chi-square is always the stat of choice. And so the chi-square is significant, less than 0.05. And for the sake of being able to do a quick little interpretation of what's going on in here, you need to add expected values into the cells. Now, those expected values are the values that would be derived purely by chance. You know, if we didn't know anything else, and there wasn't anything going on, we would assume that those would be the numbers in those cells, those different cells, purely by chance. And that comes off of looking at the totals and all that and figuring out, you know, how many are there, you know, in each one of these columns, and how much are there in each one of these rows, and, you know, multiplying the percentages and all that across to get the expected value. All right. So for this one, we expected that there would be 95 people that did not come back at the end of the first year. They weren't retained, and they had 25% adjuncts. And the actual count was 82. And so there's a variance here. There's a discrepancy between those two. So we could, you know, kind of easily say that, you know, people that had the lowest amount of adjunct instruction, you know, didn't come back, or came back more than we would have expected just by looking at those numbers. And you can go across and look at the differences, and you know, where they're a little bit bigger, that's kind of telling us something. You know, there's not so much down here because these are only, you know, well, I guess it's all about the same, but these are smaller differences because there's a bigger total that did come back. Relatively, these are smaller differences. These differences up here are a little bit larger relatively because there was a smaller total that didn't come back.
So, Dr. Bolt, on that, where the first cell is no, they didn't come back,
Yeah.
the actual count is 82. The expected count was 95.72. So what that's telling us is I guess I'm confused. More students came back than we expected?
Less.
Okay.
Yes. Because out of the group of students that only had 25%, and the ones that didn't come back, we expected to be 95.
Okay.
And there were only 82. So, well, let me think about it. You gotta, you know, these things get crossed up in your head really quickly, really easily.
Yeah, that's what I'm experiencing.
Yeah, it's kind of, okay, we expected 95 not to come back.
Okay.
82 came back. So more came back than yeah, more came back because 82 didn't come back and we expected 95. So more came back.
Okay.
Yeah, okay.
All right.
Yeah, I'm not going to be a big stickler on that one if you happen to get that one crossed up, you know, looking at one of these cells, because I mean, it really is easy to get those things turned sideways. And
Gotcha. Thank you.
yeah. You generally do a whole lot of other stuff here. Like if you discover here that there are some differences, you might generate you know, frequency charts that have, you know, kind of the complex bar charts that have you know, expected in one color and actual count in another color or something like that. So, you know, this is one where the more visual you can make it, the easier it is to interpret. And so if I were, you know, if I'm putting this in a report or something like that, I'm probably putting in a, you know, either a bar, what do they call them, a multiple bar chart or something like that, where you have, you know, side by side, you have what you expected and then you have what actually came by. And so that, you know, those things are useful because it's, you know, it's a little bit funky to try to explain this. And so there are multiple interpretations. You can just look at different levels here and whatever. So if there are interpretations to be made, you know, I'm only assuming that if you make at least one of them, it's the right interpretation, we're okay. Okay. And it's not a big miss if it's not, because it is a little bit of a confusing thing. And I've been doing it for 45 years and I still catch myself. I have to walk through it each time to figure out what's going on. And then the last thing is logistic regression. Now, remember, these are both categorical variables, but we're going to put in two factors just because it's, you know, you can put as many as you want to in here. The dependent variable is whether they graduate or not, yes or no. And you always need a dichotomous dependent variable, only two levels. And it's better if the levels are they didn't, or the status quo, and then here's the different one. Here's the change. And what the program does, it actually reinterprets these labels, and it does 0 and 1. So, you know, like in this case, it was, I think, 1 and 2. So it converted the the one, it left the one as a one, it converted the two to a zero. So zero became, they didn't graduate, one became they graduated. And so sometimes you have to reinterpret some, or recode some variables, but you won't have to worry about any of that. I mean, everything is kosher in the final, but just be aware that sometimes this is a directional statistic. And so it only goes in one direction, from 0 to 1, from status quo to the change, from not so good to great, or didn't graduate and graduated. And so graduate, yes or no, is the dependent variable. We're going to see if developmental, whether they were in developmental programs or not, and gender, or some combination of the two, had an impact on whether they graduated or not. And so we come down to the logistic regression. We are looking at the chi-square p-value, 3.733, and that's not significant. So this is not a significant, neither one of these, developmental or gender, neither one of those two are predictors of whether this group of students graduated or not. And so there's nothing really to interpret. Now, let's just say for the sake of argument that developmental in here, yeah, let's say for the sake of argument that developmental was significant, and it's the closest, so we can use that one. Well, let's say it was significant. Then we would look to see what is the odds ratio. And we're only interested in odds ratios greater than 1. And so if developmental were significant, we would say that people, now remember the way the thing was coded, 1 was graduate, 2 was not. 1 was graduate, 2 was not. So if we go in that direction, we would say that students, if it were a significant predictor, we would say that students that participated in a developmental program were 1.2 times more likely not to graduate. Now, remember, 1, it means it's 50-50. So that's not a big likelihood, and that's probably why it's not significant. But if it were significant, we could use the odds ratio to say that they were students that were in developmental programs were 1.2 times more likely not to graduate. Why? Because 1 is graduate, 2 is not.
Professor, would you ever have an instance where the p-value could be significant, but the odds ratio is less than 1?
Oh, all the time. Yeah.
But it would still be a significant difference, even though it's less than 1, the odds ratio?
Yeah, but you can't interpret it. And what people do, and what I do virtually all the time, is I take the dependent variable and I recode it. You know, I take whatever was the 1, you know, whatever was the second level, I make it the first level. And so if it were 1 and 2, maybe I make it, you know, 0 and 1. In other words, I just reverse it.
Mm-hmm.
And that changes the direction of the statistic. When I run it again, I'm probably going to find that it's still significant, although this time I will have a odds ratio greater than 1. And I can
Mhm.
interpret that way. But it's always a matter of keeping in mind the direction of the coding. And that's why I'm not going to worry too awful much about your interpretation of this, you know, on the final assessment piece, because once again, it's one of those things, if you kind of have to dwell on it sometimes. Okay, now what am I seeing here? Is what's 1, what's 2, what are the 2 different levels? Because it is so directional. It only goes, the arrow only goes one way. And that's why odds ratios of less than 1 are uninterpretable, because you don't know, you know, it's not meeting the assumptions of the statistic, because it only goes one way. Yeah. But yeah, it happens a lot that you'll realize when you put some variables in that there's more than one predictor, but they predict in different ways. You know, it's like with you know, up here with the correlation, you know, you have the sign to tell you which way it predicts. The R value will have a plus or minus. Down in the coefficients for logistic regression, the signs don't really mean much.
Mm-hmm.
I mean, you really can't use them to interpret much. And so you have to, if there's things that you're interested in knowing that you couldn't talk about because the odds ratio was less than 1, although they were significant, then, you know, my turn is always to go back in and reverse the dependent variables coding and run it again.
Okay, thank you.
Now, this is about the simplest set of basic statistics that I can give you. You know, from here it gets, you know, if you think the reading contingency tables and talking about odds ratios and all, if you think those things are really kind of twisting at your mind a little bit, some of these others you really have to be very focused on and understand how the math is working, how the equations are actually working. You know, for example, there's a way that you can calculate what is the best sample size to find significance if it's there. And so you can calculate sample size. What's the size sample that I need? And it uses a formula that has you know, things that are both looking at n and things like that. But what happens over time as the n gets bigger, the bottom starts to come up in value faster than the top, and n is in both parts of the equation. And so after a while, it creates a bias. And so you have to know that when you have to know how that particular statistic is working to understand, you know, some a little nuance of it. But these are all fairly straightforward. There's not a lot of, you know, probably the hairiest thing in here is talking about odds ratios or, you know, interpreting contingency tables. But they will answer, you know, this set of statistics here will probably answer 90% of the questions you want to know about stats. Probably working about 90% of the data set. So, yeah, I wish we had, you know, a little bit longer opportunity in the fall, which I'm assuming we might actually get to eventually. I don't know, who knows. In the fall, I'm going to teach the same course for nutrition majors, I think, over in College of Health College, Beaver College, I guess it is. And so I'll have 15 weeks. And so we'll add a couple of 3 things on the end that we don't have really time in a 10-week or so summer course to get to. So, but it's, this will work for about 90% of the stuff that you want to look at and help you interpret about 90% of the stuff that you'll find in articles. Other questions? Questions? Well, folks, you got, a couple, 3 days here, a couple of days, 3 days, I don't know. It's probably going to be Sunday before I get a chance to look at anything. So, by default, let's say you have until Sunday. And if you run into problems, whatever, you just shoot me, and you can ask a reasonably generic question. I'll respond to reasonably generic questions. And, hopefully there won't be any redos.
We'll hope.
Yeah, I mean, one of the, I will say, if you remember the very first session that I told you, the way that you learn stats and things like that is pure repetition.
That's true. You said that.
And we've gone through most of these things at least 2 or 3 times now. I think correlation, maybe the logistic regression, maybe a couple of times, and contingency table a couple of times. But most of these you've gone through more than a couple of times. And we've talked about them in different scenarios and stuff like that. So yeah, I'm assuming you'll be just fine.
Dr. Bolt, if we should have to redo a particular statistical equation or something, you'll let us know, and then we'll get a different data set from you that we should do it on, or?
You'll get a different question.
Okay.
Yeah, and once we identify if any things you're missing, if you've just gotten one wrong, one redo is not going to, it's not really worthwhile to do a redo for one. You're going to get an A anyhow if you just got one wrong. And so if you, whatever you've missed, we'll identify what you've missed. And then you'll get a new set of questions, and you're only responsible for those that you missed the first time.
Okay, and you'll let us know that.
Oh yeah, I'll let you know quickly. Yeah, it doesn't take long to really look at these because I can go down through them pretty quickly and just scan down through and yeah.
Thank you.
But you'll know by Monday morning, probably, hopefully.
Wonderful.
Okay, other questions, thoughts?
Dr. Ball,
Yeah.
I'm sorry. With the other evaluation that we had, do we need to, if you didn't get the same answers, do we need to go back and redo?
No.
Okay.
I'm hoping I answered many of the questions that you may have had about those procedures here.
Okay.
Yeah. No, it's quite possible there were 2 data sets floating around out there too. And outside of the differences between the version numbers of JASP, there were a couple of data sets, and I knew something was wrong when one of them had 192 subjects and the other one had 180. And so I don't know how that happened. I guess when I converted stuff over from last semester to this semester, I didn't catch the fact that there were 2 data sets that were named the same, and so I don't know what happened there. But in general, you either missed it badly or I wasn't going to worry about the numbers, because if you did the right processes, you should have got the right numbers for whichever data set you were working with.
Okay.
But if you did the wrong thing, hopefully this will provide some insight on that.
Okay. And we used the original data set that you posted for the final?
Yes, you did.
Okay.
Yeah.
All right. Well, thank you.
Okay. That data set's clean, I know. I agonized over that thing.
Thank you.
Yeah.
Dr. Bolt, I just have one question. I'm looking again at that chi-square example, and I know you said not to worry about this. But the categories that say expected count, that's what you anticipate you would have gotten, and the count was the actual number of people?
Yes.
Okay.
Yeah, if we did percentages here and we said, okay, of these 1,400 people here, what percent is 317 and what percent is 1107? And
Mhm.
that would give us row percentages, and we could do the same thing down the columns.
Okay.
So what percent of these two is out of 430? What percent of these two out of 411? What percent? In other words, if you got column percentages and row percentages, you could multiply row percentage times column percentage times this overall N. Where'd it go? Times this overall N, which is 24, and that would give you what these expected values are. And that's why they're not integers. That's why they're, they're decimals.
Okay.
Yeah.
And if at the, when you're doing that chi-square test, if your p-value is not significant, then
It doesn't matter.
there would be no relationship between what you're looking at.
Yeah.
And this is just telling you that there's relationships, you can't really, there's no way to identify any value to having an expected count being much lower than a count. You can just say that it is, but it doesn't mean
You can say
anything
it
else,
is.
right?
Yeah. It says these two variables are related, which means they vary in a consistent direction, the two variables.
Okay.
And the fact that they're related outside of that, that's all it tells you.
Okay.
Yeah.
So if you wanted to determine some other relationship between those groups, is there a different testing that you would do, or you just can't do anything else?
Yeah, there are.
Okay.
There are other non-parametric tests that we just don't have time to get into. I mean, I had to give you an idea, I had a doctoral course that we spent an entire semester in about a 600-page textbook on just non-parametric statistics. And there's a whole bunch of them that allow you to look at in more detail, but we just simply don't have time to.
Okay.
I need a little bit more background, to be able to do it pretty well too.
So this chi-square test is really just to look to see if there's any type of relationship, and that's the most that you would be able to determine.
Yep.
Except to indicate the accounts and the expected counts for each of the categories.
You can talk about some of that, but and that's about the simplest interpretation you can do. But it's also accurate.
Mm-hmm.
But it's not terribly sophisticated. But yeah, there are other non-parametric tests that allow us to say a bit more, but they all are limited by the fact that they're based on pure probabilities. You don't have any values from a population or anything like that you can look at. And for the other kind of test where you have a continuous variable, at least as a dependent variable, those are what are called parametric tests. Well, you can figure out the average. You can figure out the standard deviation, the standard error. You can kind of know how they should be distributed. But in contingency tests, in chi-square, you can't. You just. Okay. Now, a lot of times what we do is we'll do like a non-parametric sweep of something. Like I use logistic regression a lot just to see what's connected. And once I get a sense of what's connected, then I kind of circle back around and restructure the analysis so that now that I know what the real variables are that I've found that I can work with, I go back and do a more parametric test if I have some. I'll often take continuous dependent variables and convert them into categorical variables around the median or something like that, just to get different ways of looking at it. But and that's not 100% legit. It's just works all the time because it's really robust.
Mhm.
But yeah, I don't know. There's a lot of stuff out there. But this is a simple set, but this will get you going, and it'll interpret most of what you'll see, and it'll help you interpret most of the articles or most of the pieces of literature you're looking at.
Okay, thank you.
Okay. Other stuff, guys. If you have stats questions, after the semester, I'm not going anywhere. So, shoot me an email. I love to do stats questions because it's something that I have quite a bit of facility with, and I don't get to flex those muscles as much as I would like to sometimes. But, all right. It's been a crazy summer, but hey, you've hung in.
We got through it.
You got through it, and
At least we hope we have.
hopefully no redos. Let's shoot for no redos and kind of go from there.
All right, fantastic.
Thank you.
Having
Thank
a good
you.
rest of the
Thank
summer,
you.
good weekend, good everything.
All right, thank you, sir.
Thank
Bye-bye.
you.
Have a good one.
Thank you.